will take differentiation of inverse trigonometric function by suitable trigonometric substitution. What do you mean by that one? Suppose here is a very complicated inverse trigonometric function. For example, look here. It is tan inverse of root of 1 minus x square minus root of 1 plus x square upon root of 1 minus x square plus root of 1 plus x square. So it is in the form of tan inverse f of x. Actually, the answer is dy by dx. If it is y equals to that function, y is the function of x and y equals to like this set, and dy by dx, actually the answer is very simple. It is minus 1 upon root of 1 minus x raised to 4 into 2x. That is the answer. Is it possible to get that answer by direct differentiation by using the formula? It is in the form of tan inverse f of x. Tan inverse f of x differentiation is 1 upon 1 plus f of x the whole square into d by dx of this whole complicated f of x. This f of x is in the form of quotient formula u by v. At the same time that the differentiation of root, and simplifying that one, we should get this answer. It is highly possible that by what it is, differentiating this one by taking y equals to tan inverse f of x formula. Okay. In this case, what we do by suitable trigonometric substitutions means for x you have to take suitable trigonometric function, and this whole complicated inverse trigonometric function simplifies to the greater extent. We have studied it in inverse trigonometric function topic. Write it in the simplest form. The question was express the following inverse trigonometric function in the simplest form. It means once this function is reduced to simple form by suitable trigonometric substitution for the variable x, then differentiation can be done within 1 or 2 steps. Then you can get this particular structured answer. By direct, of course it is in the form of y equals to tan inverse f of x. You can use the differentiation formula of y equals to tan inverse f of x. You can differentiate 1 or 2 steps, you can differentiate, but you won't get, it is highly impossible to get this particular answer by simplifying it. If you are getting, it takes what it is, hours of time. But by suitable substitution, we can simplify this particular inverse trigonometric function. Means we can express this inverse trigonometric function in simplest form. Then within 1 or 2 steps, we can complete the differentiation, and we can get this particular required answer. They are asking like that: if y equals to so and so, show that dy by dx. In the examination, 3 marks and 5 marks questions will be like that. If y equals to like this, show that dy by dx is this particular answer. In CTR, questions are like that. This here 4 differentiation problems were there. If y equals to so and so, then the dy by dx is equals to like that. Okay. So then let us take it, that is what it is, inverse trigonometric function differentiation by proper substitution. I repeat, when it is necessary, if this inverse trigonometric function tan inverse f of x or sin inverse f of x, cos inverse f of x, etc., these f of x are in very complicated form. By taking suitable trigonometric substitutions for the variable x, we can simplify the inverse trigonometric function. Means we can express the inverse trigonometric function in simplest form. And then once the function is reduced to simple form, differentiation will become very simple. Okay. So for example, look here. I will demonstrate it by one particular example by taking direct differentiation as well as by taking suitable substitutions. Okay. If y equals to tan inverse of 1 minus x upon 1 plus x, show that dy by dx is equals to, show that dy by dx is equals to, it is minus 1 upon 1 plus x square. Okay, minus 1 upon 1 plus x square. I will get that dy by dx by both the method. One is by direct method and another one is by trigonometric substitution. Which one is simple, we can identify. So when trigonometric substitution is necessary, when this f of x is in very complicated form, d by dx of f of x is a complicated one, then better to take suitable trigonometric substitutions for the variable x. Okay, direct method. First one is I will do it by direct method. equals to tan inverse of 1 minus x upon 1 plus x. Differentiating with respect to x. Differentiating with respect to x, dy by dx is equals to d by dx of tan inverse of 1 minus x upon 1 plus x. Now it is in the form of tan inverse f of x. What is the f of x? 1 minus x upon 1 plus x is the f of x. Now it is equals to, what is the tan inverse f of x differentiation? 1 upon 1 plus f of x the whole square, 1 upon 1 plus f of x. F of x is what here? Which one is f of x here? F of x is 1 minus x upon 1 plus x. F of x is 1 minus x upon 1 plus x. Therefore it is 1 upon d by, what is the d by dx of tan inverse f of x? 1 upon 1 plus f of x the whole square, 1 minus x upon 1 plus x the whole square into d by dx of f of x. F of x is 1 minus x upon 1 plus x. Okay. Tan inverse f of x differentiation 1 upon 1 plus f of x the whole square into d by dx of f of x. Now I have to differentiate this particular quotient function as well as I have to simplify this particular expression. It is 1 minus x the whole square upon 1 plus x the whole square. It is not a by b the whole square, is a square upon b square. Now we will see this together. For this 1 plus x the whole square multiplies. Therefore it is 1 plus x the whole square plus 1 minus x the whole square upon 1 plus x the whole square. Okay. Into, this is in the form of u by b. Is it not? Now I have to differentiate. This 1 minus x upon 1 plus x is to be differentiated. It is in the quotient form. Numerator is having the variable x as well as denominator is also having the variable x. Therefore it is in the quotient form. Then what is the quotient formula? The denominator the whole square. In the numerator, denominator into d by dx of 1 minus x minus in the numerator, denominator into differentiation of numerator minus numerator into d by dx of denominator. Okay, is it not? The quotient formula is like this: u upon v, numerator upon denominator. Differentiation is in the denominator the whole square. In the numerator denominator into differentiation of numerator minus numerator into differentiation of denominator. Okay. Now this 1 plus x the whole square goes to the numerator. Why it is? So a upon b by c is equals to c by b. Is it not? 1 upon a by b. 1 upon a by b is equals to b by a. Therefore, this 1 plus x the whole square goes to the numerator. That is 1 plus x the whole square whole divided by c dy by dx. Differentiating with respect to x, y differentiation is dy by dx means y dash. Here it is 1 plus x the whole square plus 1 minus x the whole square. Here is the formula a plus b the whole square plus a minus b the whole square. That's equals to 2 times of a square plus b square. A shortcut formula. Otherwise you expand it. 1 square plus 2 into 1 into x, 2x plus x square a plus b the whole square. So type of shortcut formulas you have to remember, otherwise it will be costly. It costs very much in your CET examination. Okay. So nowadays students are not ready to remember the shortcut formulas. And in the CET actually, in the CET examination or JEE examination, NEET examination, the shortcut technique is very, very important. 1 plus x the whole square plus 1 minus x the whole square is 2 times of a plus b the whole square plus a minus b the whole square is equal to 2 times of a square plus b square. So there is no need to remember that formula. Just you expand a plus b the whole square, a square plus 2ab plus b square, a minus b the whole square, a square minus 2ab plus b square. 2ab cancels. Then a square plus h square, 2a square plus b square plus b square plus b square. Try to have that particular approach. By that one shortcut automatically improves. It is, therefore, it is 1 square plus 2e into 1 into x, a plus b the whole square, 2x plus 2 into 1 into x, 2x plus x square, a square plus 2ab plus b square. b square. 1 a minus b the whole square, a square, 1 square, minus 2 into 1 into x. There are also 1 into x, plus x square, a minus b the whole square, a square minus 2ab plus b square into this differentiation that is complete. The right hand side differentiation is 1 plus x the whole square, and here it is 1 plus x into 1 plus x into d by dx of 1 minus x. 1 differentiation is 0, x differentiation is 1, therefore it is 0 minus 1 minus 1 minus 1 minus x into d by dx of 1 plus x. 1 differentiation is 0, x differentiation is 1, therefore 0 plus 1, 1. Here it is 2 into 1 into x, 2 into 1 into x minus 2x plus 2x cancels, and 1 plus x the whole square, there are 1 plus x the whole square cancels. What remains? 1 plus 1 2, 1 upon 2 plus x square plus x square, 2x square, 2 plus 2x square, okay, into, here it is 1 plus x into minus 1, it is minus 1 minus x, minus 1 multiplies, here it is minus multiplies 1 into minus 1, minus of minus is plus x, okay, whole divided by, upon is cancelled already, upon is whole divided by 1 plus x square cancelled with this 1 plus x square. That's equals to here, I will take 1 2 here, x cancels, I will take 1 2 common, 1 plus x square, and here it is minus 1 minus 2, okay, so 2 and 2 cancels, and final answer is minus 1 upon 1 plus x square. I think I had done the same. Show that dy by dx is minus 1 upon 1 plus x square. So laborious one. Look here, the same procedure, same differentiation can be carried out by suitable trigonometric substitutions. By trigonometric substitution, look here. Second method, method 2, by trigonometric substitution. In trigonometric substitution, so you must be very perfect in trigonometric formulas. First year trigonometric formulas or 10th standard trigonometric formulas are very important here. By trigonometric substitution. Y equals to tan inverse of 1 minus x upon 1 plus x. I have written, show that dy by dx is minus 1 upon 1 plus x square. By this method only, I have worked out this differentiation by in mind only, by suitable trigonometric substitution, and I got the answer, and I have written it as dy by dx is minus 1 upon 1 plus x square. I have not referred any textbook. The problem is stated by myself only, and the answer I got it by trigonometric substitution only. In that substitution and differentiation is carried out in mind only. So means suitable trigonometric substitution definitely simplifies the procedure. It means okay. Let us take the substitution. Let the variable x is equals to tan theta. But you must be very perfect in trigonometry formula. Okay. Y equals to tan inverse of, in the beginning of this year class I had taken 2 hours to revise all the trigonometric formulas. Just go through those trigonometric formulas. Trigonometric formulas should be at the tip of your tongue. It is 1 minus tan theta upon 1 plus tan theta. Is it not? So what is 1 minus tan theta upon 1 plus tan theta? 1 minus tan theta, x is tan theta is taken. So for x is tan theta, 1 minus tan theta upon 1 plus tan theta. The simplification of inverse trigonometric function is already taken in inverse trigonometric function topic. Okay. So express the following inverse trigonometric function in the simplest form. That was the question. And you can expect 1, 2 or 3 marks question in that particular section in each and every final examination or in what it is your college tests. What is 1 minus tan theta upon 1 plus tan theta? That's equals to tan pi by 4 minus theta. Here is the formula, tan of pi by 4, trigonometric formula, plus r minus theta is equals to 1 plus r minus tan theta upon 1 minus or plus tan theta. Is it not? Here it is plus, here it is plus and minus, plus in the numerator, minus in the denominator, here it is minus, here it is minus, then minus in the numerator and plus in the denominator. Okay, y equals to tan inverse of, therefore it is tan pi by 4 minus theta, because numerator is minus, denominator is plus, means it is minus tan pi by 4 minus theta. This is the trigonometry formula, last year trigonometry formula. Okay, tan pi by 4 plus theta is 1 plus tan theta upon 1 minus tan theta. Tan pi by 4 minus theta is 1 minus tan theta upon 1 plus tan theta. That is, now tan inverse tan cancels. I told you inverse trigonometric function and trigonometric, same trigonometric function facing each other, cancels. Then what remains? Pi by 4 minus theta, provided this particular function have the, what it is, tan pi by 4 minus theta. This should be within its principal domain, is it not? This should be within its principal domain of minus infinity to plus infinity, but domain is not mentioned here. It means in that case we can simply take tan inverse trigonometric function and trigonometric function facing each other, cancel each other. Getting back to the original variable x, because originally the function is in the variable x. Therefore, we should return after once it is function is simplified, we should return back to the original variable and then you differentiate. So what is theta? X is tan theta, implies theta is tan inverse x. Okay, theta is what? Tan inverse x. By interchanging x and theta, inverse trigonometric function will become trigonometric function. I told you, by interchanging the variables, trigonometric function will become inverse, inverse will become trigonometric function. Is it not? That is the basic technique of inverse trigonometric function. These two variables x and theta are interchanged. Inverse will become trigonometry, trigonometric function will become inverse trigonometric function. Okay, so therefore it is pi by 4 minus tan inverse x. Now differentiation, one step. Differentiation is only a one step process. Okay, differentiating with respect to x, dy by dx is equals to d by dx of pi by 4. Whenever plus or minus is there, we have to differentiate each and every terms. Minus d by dx of tan inverse x. That's all. Even though it has consumed 4-5 steps, all steps are simple one. At the same time, without writing also you can generate the answer. That is technically very much easy. Dy by dx, despite of repeated telling, you have to work out the things in brain only. Majority of students are not doing that one and not remembering the shortcut formulas and paying the penalty in CET. It is minus, but pi by 4 is constant, in differentiation is 0, and tan inverse x differentiation is 1 upon 1 plus x square. Is it not? Tan inverse x differentiation, simple function, tan inverse x formula, differentiation of tan inverse x is 1 upon 1 plus x square. Therefore, dy by dx is equals to minus 1 upon 1 plus x. Okay, so simple it is. Process of differentiation is very simple, and even intermediate calculation is also very simple. Is it not? That is what? Differentiation of inverse trigonometric function by proper trigonometric function. So what is the intention of taking proper trigonometric substitution? To simplify the complicated inverse trigonometric function. Once the complicated inverse trigonometric function is expressed in the simplest form, then we can differentiate it within 1 or 2 steps. Okay, for every inverse trigonometric function, substitution is not necessary. For example, what are the problems given in the previous class? Sin inverse x by 2, cos inverse x square. For those things, for those inverse trigonometric functions, substitution is not necessary. Directly you can differentiate. Whenever inside function is f of x is complicated one, direct differentiation is laborious one, lengthy one, then you have to take proper substitutions. Once proper substitution is taken, function reduces to simple form, then differentiation process will become simple. Okay? By direct method and by substitution method, how the process can be simplified is demonstrated in the previous example. Find dy by dx. Find dy by dx in the following examples. Okay, first one, y is equals to, they are not mentioning, the examination they are not mentioning, find dy by dx by proper trigonometric substitution they are not mentioning. We have to understand it is by trigonometric substitutions only. This some inverse trigonometric function by trigonometric substitution, the functions like cos inverse x square etc. by direct method. We have to take proper method, direct method or substitution method. It is left to us, choice is left to us. Okay. If function f of x is complicated one, then the substitution is inevitable, but they are not mentioned by trigonometric substitution. Find dy by dx by trigonometric substitution, they are not mentioned. Okay, tan inverse of 3x minus x cube upon 1 minus 3x square. First one. Second one, y is equals to cos inverse of 1 minus x square upon 1 plus x square. I think this is given as a homework for you. Third one, in the textbook it is given 0 less than x less than 1. The inverse trigonometric function, one is inverse trigonometric function, the domain x ranges from 0 to 1. Okay. This is actually why solving the problem. This range is not necessary for us. But sometimes for 1 marks in CET as well as in theory examination, they are asking y equals to cos inverse of 1 minus x square upon 1 plus x square. Then the x value, x lies between 0 to 1. The answer is then x belongs to the interval of x is the domain x lies in. The domain set of x's lies in. The correct statement. Okay. Third one, y equals to cos inverse of 2x upon 1 plus x square. Here also the domain set, the set of domain contains x's, x lies between minus 1 to plus 1. Fourth one, y is equals to, it is 6 sin inverse of 2x into root of 1 minus x square. Okay, here x lies between minus 1 by root 2 less than x less than 1 root. Okay, these are the ranges of x, means x lies between these values, then only these functions are valid one, otherwise these functions are invalid. It will not be a function. For other values of x, this y equals to sin inverse 2x into root of 1 minus x square will not be a function. Okay, so let us take one by one. First one is y equals to tan inverse of y equals to tan inverse of 3x minus 3x upon 1 minus 3x square. Here it is x is equals to again tan theta. Mind it, one don't have the one wrong impression. If tan inverse is there, the next should be tan theta. Cos inverse is there, the next is cos theta. Sec inverse is there, the next is sec theta. Not like that. The substitution is not like that. Okay. So, but sometimes it coincides. Outside tan inverse, x is also tan theta for the previous problem and this problem also. It has coincided actually, but it is not the general rule. If it is tan inverse, the next should be tan theta. If it is sec inverse, the next should be sec theta. Not like that. Okay. Therefore, y equals to tan inverse of 3 tan theta minus tan, x is tan theta, no? X cube is tan theta, the whole cube, tan theta the whole cube is tan cube theta. Okay. In trigonometric function, if trigonometric function whole raised to n is there, then n can be taken inside just before of theta. Okay. Tan theta raised to tan raised to 10 theta. Tan theta raised to 3, tan raised to 3 theta. Okay, tan cube theta upon 1 minus 3, x is tan theta the whole square is tan square theta. Okay, tan theta raised to n is equals to tan raised to n theta. Okay, in general, it holds for all trigonometric functions. Sin theta raised to n is sin raised to n theta. Just before of theta, the raised to n should be taken. Okay, what is this one? 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta. Recall the trigonometric formula. I told you trigonometric formula should be very essential here in differentiation as well as in integration. not only in differentiation and integration, in even algebra also, in determinants we have seen that one, okay, in determinant matrices and sets relation function. There also we need the trigonometric formulas, first year trigonometric formulas, 3 tan theta minus tan cube theta upon minus 3 tan square theta. Prepare the chart of, already it is given, already in the beginning it is given, so just prepare a chart of the trigonometric function results and just revise it again and again. By revising it twice or thrice, it will become perfect. It is tan inverse of, it is 3 tan theta minus tan cube theta upon minus 3 tan square theta is tan 3 theta. Example, tan 3 theta formula. Tan 3 theta is 3 tan theta minus tan 2 theta upon minus 3 tan square theta. It is the tan 3 theta formula. It is not sin 3 theta, is 3 sin theta minus 4 sin cube theta. Cos 3 theta is 4 cos cube theta minus 3 cos theta. Is it not? So therefore, tan inverse tan cancels 3 theta. What is the theta? When x is tan theta, x is tan theta implies by interchanging x and theta, theta is equals to tan inverse x by interchanging x and theta. Inverse trigonometric will become trigonometric function y is equal to 3 theta, that is y equals to 3 into theta. Theta is tan inverse x. Now differentiating with respect to x. Look here. Direct differentiation is highly impossible to get this answer. Dy by dx is equals to 3 constant outside. Differentiation of tan inverse x is 1 upon 1 plus x square. It is directly upon 1 plus x square. I have written it directly. 3 into dy by dx of tan inverse x. Tan inverse x differentiation is 1 upon 1 plus x square. Otherwise you write it. 3 into dy by dx of tan inverse x. That's equals to 3 into 1 upon 1 plus x square. That is 3 upon 1 plus x square. Without writing all these things, if you have written 3 upon 1 plus x square, and you are getting the full marks, this is actually unnecessary for the examination. And other 2 are homework for you. Okay, other 3 are homework for you. I will tell you how to do. Y equals to cos inverse 1 minus x square upon 1 plus x square. No need of any trigonometric substitution. Already ready-made formula is there. Y is equals to cos inverse of 1 minus x square upon 1 plus x square. So that is the standard formula. That's equals to 2 tan inverse x. Is it not? That's equals to 2 tan inverse x. Therefore, no need of any trigonometric substitution here for this problem. You take it as y equals to 2 tan inverse x. Then differentiating with respect to x, we get dy by dx is 2 upon 1 plus x square. Okay. And next one is y equals to sin inverse of 1 minus x square upon, cos inverse of 2x upon 1 plus x square. Actually, sin inverse 2x upon 1 plus x square is what it is? 2 tan inverse x. Therefore, but we have to use the result sin inverse x plus cos inverse x is 1. Pi by 2. Sin inverse x plus cos inverse x is pi by 2. Therefore, cos inverse 2x upon 1 plus x square is pi by 2 minus sin inverse 2x upon 1 plus x square. Okay. Then differentiate. Sin inverse 2x upon 1 plus x square is 2 tan inverse x. Then by differentiating, you will get the answer as, so it is dy by dx is minus 2 upon 1 plus x square. And last, third one, y equals to sin inverse 2x upon root of 1 minus x square. Proper substitution is, x is you take it as cos theta, then 2 cos theta into root of 1 minus cos square theta. 1 minus cos square theta is sin square theta. Root of sin square theta is sin theta. 2 times of sin theta cos theta. Sin 2 theta. Sin inverse of sin 2 theta. 2 theta. Theta is cos inverse x. Then y equals to cos inverse of cos inverse x. That's equals to x. Then dy by dx is 1. I'm sorry, just let's see. But for the next one, sin inverse of 2x upon root of 1 minus x square, the proper substitution is either you take x is equals to sin theta or x is equals to cos theta. Okay, and use the formula. Sin 2 theta is 2 times of sin theta cos theta. Root of 1 minus cos square theta is sin square theta. Root of 1 minus sin square theta is cos square theta. You have given the hint. Try to solve it. In the next class, I will solve these problems once again.